to go into a greater effort to understand what couldn't have happened in this building for its destruction, I'd like to bring up one of the top forensic structural engineers in the country from the University of Alaska, Professor Leroy Hulsey, structural engineer, PhD. Professor Hulsey?
Good afternoon. Do I push this down?
No.
Okay. Good afternoon. It's a pleasure to be here today, and thank you all for giving me the opportunity to be here. Under forensic structural engineer up above, it says Las Vegas, Nevada. That's not true. Fairbanks, Alaska is true. So I want to just kind of give you a little bit of an insight of who I am and kind of give you some background before I get into this presentation. I'm actually also a licensed structural engineer. I have been in the business some 40 years. I've worked on, as an expert, the Avenues of America building, the United Nations building, the Dean Dome in North Carolina, and a number of other structures around the country. So what I'm bringing to this presentation is the fact that I've done a lot of work on structural investigations, and so when I was asked to do this, to investigate the collapse of the World Trade Center 7, I thought it was quite an honor, and I've put together a team that I feel is really, really good. Dr. Fang Xiao, who is a postdoctoral researcher who did his PhD under my work, and then Zili Kwan, who is a PhD student now, and because of this project, I've redirected his research effort, and he's going to be looking at fires on high-rise buildings and particularly steel structures. So that being said, let me take you to this first slide and focus your attention onto the blue outline. And we're looking at the plan view of the floor 13. Column 79 is not identified there, but you see column 76 and 78. And if you remember that picture of the building falling a moment ago, that if we rotate this 180 degrees and put the blue on the left and the stuff on the right, that blue area represents the NIST's approximation of connections for this building. The portion on the left of this plan view, they chose not to put any of the connections into their finite element model, which indicates that the section to the left is much stiffer than the section to your right. Furthermore, they didn't approximate the stiffness of the connectors on the exterior part of the building. Now, what does that physically mean to you and I? What it means is when you heat up a bar, the bar is going to try to elongate. And it will elongate without resistance, no matter what, unless there's some place that's stiffer than another. If it's fixed on one end and free on the other, it's going to move to the right, imagining fixed being on your left. If I was to put fixed on your right and free on your left, it would expand to your left. Now, if I fix it on both ends, it can literally tear itself apart with a fairly low temperature. So here's the situation on this building. When NIST modeled it, they did not model it correctly because there are connections everywhere. And so that means part of this building was treated more stiff than the other part. And if remember when you saw the thing come down, what happened is part of the building was coming down differently than the other part. That should have given them a clue right away. That's not what really happened. Take a look at this picture right here. See that red line down? The left part is where they modeled the connections. The right part, they did not. So the left part, when it starts to fall, is coming down fairly rapidly, but the right part is really, really stiff. And so it's not anywhere simulating what really happened in the real building. So that immediately should have told them that this model that they were trying to use to argue that the fire brought this building down was wrong right away. And from the first time I saw this, I was wondering, what in the world is wrong with this model? And it wasn't until a few weeks ago we identified the real cause of this. And that's through this process, because we've modeled every connection. So let's examine the NIST approach for a moment. They've said there's more than 5.5 inches of movement at that girder to push it off the bearing, and so that the column was no longer resisted there. Well, you can imagine that being real stiff on one side, the amount of movement that was occurring was going to accumulate over that length, whereas actually the more stiffer part is near column 79. It didn't move hardly at all. So the issues that led to that 5.5-inch movement primarily were due to the fact that they didn't model the connections properly. And there's some question in my mind about, even in the place where they did model the connections, they were not connected and properly substructured within the model itself. And I realize I may be using words that you're not familiar with, and I apologize for that. But what I'm really trying to say is that in the real structure, they had bolts and they had these connections putting beams to girders and so forth. And on part of their model, they didn't include those. On the other part, they did, or they attempted to. We did everywhere. So they also so the issues that led to the 5.5 inches of movement and more, it was actually more than that, was they treated the non-composite, the girders, as non-composite. In other words, what they did when they looked at the thermal expansion, they didn't include the concrete slab in it. That was totally wrong. They separated the connection modeling. That was wrong. They missed the wide flange stiffeners. That was wrong. So giving you kind of a comparative narrative of what we did versus what they did, our floor framing steel connections were addressed by using the word springs. That basically, there's some resistance to the bolt and how that is resisting movement up and down, and there's some resistance to rotation and all that kind of stuff. We addressed that in these connectors. So in this table, you'll see they did it partially, in other words, over part of the floor system. We did it everywhere. Exterior steel framing connections were included by us, but were not by them. In other words, there was a sense of stiffness that was not correct. Girder to column stiffener plates were included by us, not by them. The floor composite with beams, we included, we said they were composite. We also said they were not composite. We wanted to look at all extremes to make a comparison between whether we could simulate what they did or not. The floors with composite beams and girders were examined by us, yes, not by them. And by the way, I think you can imagine that even if they were not composite, the concrete deck is fairly heavy. It's going to be setting on the beams and the girders, and so to slide the concrete with respect to the steel, there's a lot of friction. And so it's going to take a huge amount of effort to make that happen, to slide without those two working together. And our analysis shows that that couldn't have happened. Okay? The thermal expansion of the concrete deck was included by us. It was not by them. Thermal conductivity expansion for the material properties, we included what we believe to be the aggregate that was used in the construction, and the aggregate type significantly affects the thermal conductivity and the thermal expansion of the concrete. So we tried to make sure that we had an understanding of what may have occurred truly on that day. The thermal horizontal movement of column 79 was, it was more than 5.5 inches. I gave them credit here. It was more than that. But it was less than 2 inches by us. And let me also share with you this. We had a quality control program on every single day. My students, my PhD, my doctoral graduate and my PhD student, we meet every single day. We talk about what we've done. We criticize each other's effort. We make sure that we can justify every piece scientifically. And then, and so as part of this, we use 2 different computer finite element programs, 2 different ones. And we did that for a reason. We cross-checked each other's work through looking at each other's models, And then we also ran them using 2 different programs. One of these gave us 1.9 some inches plus inches, and the other one was 1.85 inches instead of the 2 inches. That's why I said it's, so both programs gave us less than 2 inches.
Dr. Fossey, let me ask you a question. That you've listed here for us 8 or 10 very specific things that they didn't do or that they did incorrectly. Based on your own professional judgment, do you think that that falls within the realm of simple incompetence, or do you believe that this demonstrates a pattern that is so gross that it had to have been done intentionally?
I don't know the answer to that. I don't know how anybody could think that this was a cover-up and know anything about finite elements and know structural engineering to think that they could get away with that.
Right, but if one of your PhD students submitted this to you, would you have flunked them?
Yes.
We're going to go straight to this slide now, and I got to go on.
Okay. So my answer to you today is that the fire did not bring this building down. Thank you all for giving me the opportunity to present for you.
Can we ask a question? Can we ask a question?
Yeah.
Would it be all right?
Yes.
Can't hear you.
I want to stress that the NIST report regarding the World Trade Center 7, have you studied this the part of the report? Other firms state that the collapse fell was due to the thermal expansion of the structural steel. And after it all, that the World Trade Center 7 fell because of the fires provoked by the diesel fuel and from debris. Do you think that it is possible that it was there is a cause between the a connection between the fire expansion and the fall of the World Trade Center 7? What do you think about this affirmation statement of NIST? Have you read this?
If I understood what you're saying correctly, I do not believe that there is any possibility that could have happened that way.
Let me ask this: if you could, on a scale of 1 to 100, what do you think the possibility is of this particular building failing with the data with regard to these specific fires? On a scale of 1 to 100, how probable do you think it is, or how possible do you think it is that this building could have collapsed simply because of the fires?
0.
Yeah, if you could, it's like, my reaction to what you've had to say is, of course. And in fact, as soon as you were given the problem of trying to just study, why this building went down, it seems like you didn't really need to do anything. You could have looked at the video and seen and come to a conclusion at that time. Wouldn't you agree that that's true?
I would agree that I knew that there was something wrong with that computer model.
Okay.
I did not know I did not know whether it was a fire-related issue or not.
All right. What I'm asking you is, you knew that was controlled demolition as soon as you saw it the first time.
I can't say that, and I won't even say that yet today.
Okay. So you were allowing for the possibility that building came down as a result of something other than controlled demolition. Is that what you're saying?
What I said from the day one when I took this on is that I may not be able to tell you what brought it down, but I'll tell you what didn't bring it down.
Okay. So, but I'm not. it seems to me that it's obvious simply from looking at the video that that's controlled demolition. Dan Rather didn't make that up, because he was being creative. He was reacting to his knowledge of life and his views of these things happening for as many times as he'd seen them. And I want to know if that was not your state of mind when you took on this problem.
Let me be very clear. I have a requirement to put away whatever my feelings might be and present to you pure science on what we're going to end up with. So we're not done with this. What we're going to look at are a lot of possible scenarios that may bring this building down, including pulling out columns as we move forth in the next few months. I will be able to tell you, when I get through this process, a lot more about this issue. And then it'll be based on a science answer, not on my feelings.
Professor, thank you very much. We've got to move on. Thank you, Dr. Halsey. Thank you.